Welcome to the NHERI SimCenter's Live Expert Tips. In this session, we introduce you to a new open source framework for interdependent resilience simulations. We are thrilled to have Dr. Nikola Blagojević introducing this topic. Nikola is a postdoctoral researcher at the Chair of Structural Dynamics and Earthquake Engineering at ETH Zurich. His research focuses on the development of novel tools and frameworks for disaster resilience assessment of interdependent systems. As part of his doctoral thesis, he developed the iRe-CoDeS framework for probabilistic resilience-based design of the built environment. His current work involves using the iRe-CoDeS framework to assess hospital resilience. He is the lead developer of the open source Python library for regional recovery simulation and resilience assessment, pyrecodes. He holds a PhD from ETH Zurich. And Nikola, thank you for being here.
Of course, thank you. Thanks a lot for organizing everything and for the introduction and for the invitation. It's really great to participate in one of these, not only listen. So let me see. Okay, so as you already said, I'm going to talk about pyrecodes today. And the reason I'm talking about it at the SimCenter LET is because we plan to integrate pyrecodes with SimCenter tools. And I'll also show an example of how you can do that. But here's the outline of my presentation. It's going to be around 40 minutes. I'm going to start with the motivation. So why are we working on these tools? And then I'm going to present the iRe-CoDeS framework briefly, which is the basis for the pyrecodes software, which I'll present next. And then I'll present two examples on how you can use pyrecodes to assess regional resilience of interdependent systems and how you can use pyrecodes together with R2D to extend R2D's capabilities to recovery modeling and resilience assessment. And in the end, I will be very happy to answer any questions which you might have. So let me start with the motivation. As you can see from recent disasters, which are getting more severe and more frequent, is that no matter how much we try, we still have damage in our built environment. This has been shown in the earthquake in Turkey, earthquakes in the Balkans, in Japan, and also if you look at flooding in Germany, we still have some building damage. So even though we try hard to engineer our structures to be robust to various disastrous events, we still experience damage. And what we are now thinking about is, okay, damage is obviously inevitable right now, but how can we then reduce disaster losses? So what we can do, we can start focusing on recovery. So we have to accept that a certain level of damage is going to occur, but we can start designing our built environment to be able to quickly recover following this disasters and this damage that's going to be there. And this is where the concept of resilience comes in. So for us, resilience is the ability of a certain system to quickly regain functionality following a certain disruption. And when we talk about the built environment, what we have today, what we already use are the tools to assess the robustness and the redundancy of our structures, of our bridges, our networks, our buildings, and so on. But what we are lacking to cover this whole timeline here are tools to simulate recovery of these structures and these systems once they have a certain decrease in their functionality. And this is where the iRe-CoDeS framework steps in together with the pyrecodes software. So what we're trying to do with iRe-CoDeS is to simulate recovery to fill this missing piece, and then also quantify resilience by explicitly measuring functionality of these systems using the concepts of supply and demand. And we hope for this to become something that's going to be used in practice in the future. So how would an iRe-CoDeS model look like? If you have a certain system, let's say a city, which is a complex system of interdependent systems, such as the city of Zurich here, the first thing we're going to do, we're going to discretize this system into components. These components can be bridges, can be buildings, power plants, water pumps, and so on. So components coming from many different interdependent systems. But although they all operate in different ways, what is common to all of them is that they're all supplying a certain resource to the community, but also in turn requesting other resources to operate. That's their demand. And what we want to know in the iRe-CoDeS framework is how are these supply and demand characteristics of each of these components going to change after they experience damage and as they're being repaired. Then the way in which we can capture these interdependencies among these components once again using supply and demand, is by simulating the flow of resources among components at different time periods after the event, and trying to figure out how much of their demand can be met by the currently available supply. If the component's demand is not fully met, we decrease the component's ability to provide supply to its users, and this can cause cascading effects, which we can also capture in the iRe-CoDeS framework. So apart from using concept of supply and demand to capture interdependencies, we also use them to quantify resilience. And what we do, we aggregate component level values on the regional or the system level to capture the change in the system level supply of, let's say, housing or electric power or potable water. Apart from supply, we also take a look at the demand, because the demand can also change. You can have a decrease in demand for, let's say, for electric power if people leave the community because buildings are damaged. But more importantly, you can have an increase in demand because, for example, you have emergency calls, so an increase in demand for communication services, or an increase in demand for construction workers, for building materials, because these things are needed to rebuild the affected regions. Once we simulate the flow of resources from suppliers to users, and we take into account the transportation losses, different allocation strategies, we estimate the consumption or the met demand of components. So how much of these resources actually reach the end user. And then the way in which we're going to quantify resilience is we're going to take a look at the difference between the total demand for a certain resource and the actual met demand for this resource. And this is what we call lack of resilience. So for us, if there is a lot of unmet demand following a certain disaster, then the system providing this resource is not very resilient. Apart from using this integrated unmet demand, we can also use the same concepts to link the iRe-CoDeS resilience assessment with the NHERI community resilience goals, which say that for if you have a community, you need to define these goals, and the format of these goals is you need to achieve a certain functionality level of a certain system, let's say building stock or educational systems, within a certain time following the event. And what we do in iRe-CoDeS, we say our definition of functionality is the percent of met demand. So we can assess how much time a certain system needed to achieve a certain percent of met demand, i.e. a certain functionality level. And then this can tell us if this system can meet its resilience goals or not. So this is how we want to quantify resilience. But now what we need to somehow simulate or estimate these supply, demand, and consumption curves for different resources in our cities. And the way to do this is to use a computational workflow, which is we try to make it as much as possible physics-based and modular. And this extends the classical tools used in catastrophe modeling, which use the hazard module, the vulnerability module, and the exposure data. And then they're used to assess repair costs or casualties. But what we do, we extend this workflow by putting in the recovery module, which simulates the recovery of these components from this estimated initial damage. And finally, we quantify resilience. So basically, iRe-CoDeS covers these two modules here. So if you want to use iRe-CoDeS, you do need to have other modules giving you the initial damage of your built environment. And this is what we're going to use R2D2 for. So now I'm going to start with a brief overview of iRe-CoDeS. iRe-CoDeS is an implementation of the iRe-CoDeS framework. It's object-oriented. It's written in Python. It's open source. And the way in which it's designed is to be extensible and modular, so you can plug in your own models for individual systems or for different hazard and vulnerability models. And it's basically designed to extend these existing regional risk assessment tools. Right now, it's in its beta version, the first one, and development is in progress. If you have any comments, suggestions, or you would like to work on iRe-CoDeS, I would be very happy to support. And here, what I want to start with first is the object-oriented architecture of iRe-CoDeS. So you can see here the more important classes and how they are related to each other. And let's say the central class is called the system class. This class contains all the components and the ways in which resources are distributed. And this is where you're going to run your resilience assessment from. Now, the way in which you're going to create the system class can be very, very different depending on the data which you're using. So to do this, we have the system creator class, which is creating the system for you. And right now there are two implementations. There is implementation which uses a JSON file to create the entire system. And then there is the other system creator class, which uses the outputs from R2D tool, plus a certain other JSON file to create the system. If we talk about components, there are currently 3 classes of components. The standard iRe-CoDeS component, which is most commonly used, but you can also, if you want, use the residential building class, which also includes the increase in demand for communication services due to emergency calls. And you also have the infrastructure interface class, which is used to plug in the outputs of third-party infrastructure simulators into pyrecodes. Each of these components has its own component recovery model, which is central for assessing how supply and demand change over time. And you can use many different component recovery models in pyrecodes. You can use very simple ones, such as the ones proposed in HASUS when you have a single parameter describing recovery, which is the recovery time. But you can also go into something more detailed, such as a Reddit type of a recovery model, or you can also condition the progress of each of these recovery activities, as we call them, that can be impeding factors or repair. You can condition them on the availability of resources, so you can capture resource constraints related to recovery. When we talk about resource distribution models, which are used to simulate the flow of resources from suppliers to users and estimate consumption and account for interdependencies, we have 3 different resource distribution models. The ones which is used most commonly is the utility resource distribution model. And here we can also plug in other ones. There is Winter, there is PipeSet, there is Panda Power. I'll talk a bit about this later on. Right now, these are very simple, I would say primitive, but there is a way to extend pyrecodes in this direction. And then when we talk about quantifying resilience, there is a separate class called Resilience Calculator, which is right now we have 2 implementations. One is related to NIST goals, so you can assess NIST goals using pyrecodes. The other one is related to the original, let's say, RE-CoDeS framework, which calculates the integrated unmet demand of a certain resource during the whole recovery period. So this was the object-oriented architecture, but the way in which the algorithm runs once you run the resilience assessment is outlined here. So the first step is you assign component damage. And then for each recovery time step, first you update component state to understand how much supply and demand the component currently has. Then you distribute resources, you decrease the supply of those components that don't get enough demand, that don't have enough resources to operate. And then finally you recover components also conditioned on how many resources they got, for example, how many workers, how many engineers, and so on. And you repeat this until you finish with recovery, and then you calculate resilience within the resilience calculator class. So how do you construct a pyrecodes model? The first step, there are basically 5 steps, but the first 3 are the most significant ones. The first step is you need to somehow discretize your system into localities. Localities are like neighborhoods that can house some components. So you need to decide how you want to cut up your region and which components you want to consider. These components can be located in localities, but they can also connect localities if there are links. And then what you do, you need to define the component library file, which is a JSON file in which you provide the common parameters for the component types. I'll explain how this works in detail when we talk about the examples. Then you define the system configuration file, which is another JSON file where you define the content of localities. You define how the damage data is provided, what are the resources considered, the resilience calculators you would like to use, and the constants which are applied to the entire system. And once you do this, this is the major part of things which you need to define. Then you define the main file, which just points to the location of the system configuration and component library file, and you're ready to run the pyrecodes assessment. So right now, if you go to the GitHub repository, I'll provide a link later, you're going to see that we have 4 examples on how you can use pyrecodes. These go from very simple ones to more complex ones. And here I'll briefly present 2 of them. So I'll start with example 2 from the pyrecodes webpage, which is a virtual community with 3 interdependent infrastructure systems. And the idea was to assess the disaster resilience of this virtual community. Damage input is provided as a text file. What I've used in some papers, I've used HASUS to get the damage data for these components, but what I provide now on the webpage is a file with some random damage levels just to test if this works properly. And we have the power, water, and communication systems, which all rely on each other to operate. And then if they operate, they provide resources to 9 residential buildings located in this community. So as I said, step 1, you need to define components which you want to look at and how they're grouped in localities. This is very simple in this example because it's a virtual community which was made compatible with iRe-CoDeS from the start. You can see here these circles, there are localities. Some of them contain components, others just serve as intersection for these links here to make the network a bit redundant. We have some bridges, power plants, here the building stock units, base transceiver stations, and so on. Then step 2 would be to define the component library file. So here you can see the list of all components which are considered in this example, and you need to define one section per each component. And the way in which this section would look like is outlined here. You have all of this also on pyrecodes webpage. The point is you have the component class, the recovery model of the component, and then component supply and demand parameters. Now let's see how this looks like for a power plant in this example. So here you can see this is the name of the component. The component class is a standard iRe-CoDeS component, which is most often used. The recovery model, you can see the name of the class, and here you can see the parameters. Because we are not considering impeding factors, we jump immediately to repair. So we assume repair starts immediately after the disaster, which is a bit optimistic, but this is just a virtual example. So here you can see we have an activity called repair. Its duration is 100 time steps. Time step is something that you need to define for yourself. In most of our examples, time step is a day. And then you define the damage functionality relation. So how is the damage level of this component going to relate to its functionality? In this case, we have a reverse linear relation, which means that as damage goes down at every time step due to repairs, the functionality linearly increases. And then this functionality is going to affect the supply and the demand of the component, which you define next. So supply, this component provides electric power. The amount is 40 megawatts, and the functionality to amount relation needs to be defined. So how is functionality affecting the supply, and also how is unmet demand affecting this supply, because this is how we capture interdependencies. And here you can see that, for example, unmet demand to amount relation is binary. In this case, this means as soon as you have 1% of unmet demand for any resource, the supply is going to be 0. There is also a relation class in pyrecodes which defines all of these relations, which I'm using here. For the operation demand, these are the resources this component needs to operate. We have electric power as well, communication and cooling water. They all have their initial amounts, and you also have the relation on how they're linked to the functionality level of the component. And as I mentioned before, you need to define such parameters for each of these components. Of course, there's a lot of copy-paste when you do this, so it's not that difficult. Now we move to the system configuration file, which is a bit longer, and it has 5 sections. So there are constants, content, damage input, resource, and a resilience calculator. And now I'm going to step through each one of them for this example. So when we talk about constants in this example too, it's quite simple. You define the starting time step. So when the recovery is going to start, the maximum time step. This is when the recovery finishes, no matter, regardless of the damage of the components, so that you don't have infinite recovery in your simulations. And then you have the disaster time step. This is when the disaster is happening in your simulation, when is damage assigned to components. And then content section of the system configuration file consists of a couple of sections like this one here, where each one defines what you have in a locality. So for example, locality 103, these are the coordinates of the locality, of the center of the locality. These are the components in locality. And here you describe which links go from this locality to other localities. Here you can see, for example, that from locality 103 to locality 102, we have a transmission line, potable water pipe, and a cooling water pipe. And then damage input is provided by the file damage input class. And here you link the parameters, the location of the damage input file. You can see how it looks like here. And then you define the resources. Resources here, you can see the electric power. This is the group of resources to which this resource belongs to. This is only for users to make it easier for them, because you can have a lot of resources, but it's not really used in the code right now. And then you define the distribution model. Here we're going to be using the utility distribution model, and the parameters for this model are the distribution priorities. So how are we going to prioritize components when we start sending out power? And in this case, we're using the component type based priority class, which means that we're going to first start from the power plants, then we're going to send the electricity to base station controllers, and so on. So we prioritize based on the component type. There are also different distribution priority classes in pyrecodes. I'll talk about another one in this next example. And here you define which transfer service is going to condition the distribution of power. These are electric power transfer services, which are provided by the transmission lines. So if you have a damaged transmission line, there is no path between two localities in terms of a functional transmission line path, let's call it like that, you won't be able to transmit power. So we also capture this in this example. And then the final part is the resilience calculator. Here we implemented both classes which are currently available, the iRe-CoDeS resilience calculator. You can define the scope. Do you want to take a look at single localities, at certain components, or do you want to look at the whole system? And for which resource you want to calculate this total unmet demand. You define it here. And then you also define the NIST goals resilience calculators. You define which resource you want to look at and what's the functionality level that you're going to be measuring the time to achieve to. Once you do this, most of the things are done. Step 4 is a very small step. You define the main file in which you specify the location of the component library file and the class used to instantiate component library. Right now, there's a single one, so there's not a lot of choice here. You use the JSON component library creator, which takes the JSON file, which we defined in step 2, and then creates the component library, which then creates our components. And then for the system, we have the system creator class. So you need to tell pyrecodes which creator to use to instantiate the system, and then what system class we want to use for the system. Right now, this is the single one we have. And then you provide the location of the system configuration file. Step 5 is running what you already defined. This should be very easy to do. So once you install pyrecodes, you can pip install it. You can also clone it from the GitHub repository. You type from pyrecodes import the main module, main.run, provide the location of the main file, and that's it. Once the simulation is finished, system.calculate resilience, and you're going to get resilience outputs. Now that you can run this in your own Python script. You can run it in a Jupyter notebook, these Jupyter notebooks are available on GitHub, and you can also use Google Colab if you don't want to don't want to set up anything, don't want to install anything, you just want to see how it works. You can go to the Google Colab notebooks, also available on GitHub repository, and just run it immediately. And this is what you get as the output. So there are two parts to the output. One is textual output. Here you can see from the iRe-CoDeS resilience calculator, which has the scope all. This is the total unmet demand, basically this whole area under the curve. And these are the values. Some people can, for example, say that what's the cost of an undelivered megawatt of electric power? This cost times this amount here, you get the total cost related to this lack of resilience of the electric power system. The other way, the other output is going to be the NIST resilience goals calculator, which tells you, for example, what was the time needed to reach this functionality level of 95% for the electric power system. In this case, it was 22 time step or 22 days. And of course, this is equivalent for all the other resources. The other way in which you can output the results is to plot them. There is the plotter class in pyrecodes, which does this for you. And you can see how you can use it in the examples on GitHub. So here you can see, for example, the supply and demand for electric power, how it changed after this virtual disaster. And this is your unmet demand here. You can also plot Gantt charts to see how your individual components recovered. In this case, it's a bit trivial. In future examples, it's going to be a bit more interesting. And so now I'll jump to the next example. Example 3, this is where I'm going to show how you can link R2D with pyrecodes. And in example 3, what we wanted to do, we wanted to assess seismic resilience of housing in Northeast San Francisco. And we took the 7.2 magnitude earthquake, which is defined basically in example 1 from R2D. So this whole example 3 of pyrecodes relies on example 1 from R2D, which uses basic hazard calculations, but also provides exposure data and the resulting damage of all of our buildings. You can run it also in the graphical interface. And then what we wanted to see is how quickly is the housing or shelter, as we call it here, going to recover following this event. So how do we do this? Step 1, define components and localities. So locality 1, in this case, is a single locality because we didn't look at any links. We just looked at residential buildings in this example. So we didn't need to divide this into neighborhoods and define links between the neighborhoods. And all of our components are residential buildings. Next step is to define the component library file. So here you can see that every building in different damage state, as defined by Hazus, has a separate component library entry because they're assumed to have different recovery activities, as you can see here. Apart from all of these buildings, we also have the emergency response center, which is sort of a hub for distributing recovery resources. This is sort of simplification, but this emergency response center provides all the engineers, all the workers, all the demolition teams, and so on. And here you can see the more damage there is, the more complicated the recovery, more activities, more resources needed, and so on. So I'm going to here show briefly how you can implement this for a building in damage state 1. You can see there are 3 activities, which are all resource constrained. So they only start once this component receives sufficient resources for this activity. And the way in which we're going to define this component is shown here. So this is called the DS1 residential building. Once again, standard iRe-CoDeS component is the class we're going to be using. And here you can see the recovery model parameters, which are now a bit longer than before. So what you define the rapid inspection as the first event. You define the duration of rapid inspection, which is set as a log normal distribution with a dispersion of 0, so basically a deterministic value, and has a median of 1 day. And the demand which is needed to start rapid inspection is the first responder engineer. And you need 0.1, 10% of first respond engineers a day, because the unit here is, let's say, engineer day. So 10% of engineers a day is needed for a single building. And then there are no preceding activities. So this starts immediately after the damage is assigned, if an engineer is assigned to this building. Then you define contractor mobilization, which now has a slightly longer duration, 7 days with a dispersion of 0.2. The demand is a contractor. 1 contractor is needed to start this, and the preceding activity is rapid inspection. Same thing for repair. And then we jump onto damage functionality relation. I wanted to show DS1 because I think this is important. Here you can see damage functionality relation is constant. So what does this mean? It means that no matter what the damage of this building is, functionality is at 100%. This means that if you have a damage state 1 building, it can always be housed after the event, because damage state 1 usually means some smaller cracks in the plaster, not major. People can still stay in their buildings, but despite that, we still have some damage which requires some repairs, and these repairs do require some resources which are taken from other buildings as well. So we need to consider this. And then we define the supply and demand. Supply, this building supply shelter, and here you can see that the amount is 0. Why 0? Well, because what we're going to be doing here, we assign these template, these default values, let's say, and then as we are creating systems and as we are reading the information from R2D, we're going to see what is the floor area for each building, and then we're going to assign the population of each building condition on the floor area. So these amounts are actually assigned a bit later when the system is created. And here, once again, we need to define the functionality to amount relation, which is now a bit irrelevant because the functionality is constant, and the operation demand is actually also shelter, because we assume that the demand from this building comes from the people that were living in this building. So they all want to go back to the same building which they populated before the earthquake. So we define basically people as the demand for shelter in each building. And then we can jump to the system configuration file. Once again, 5 sections. And here it's slightly more complex than before. Constants, we still have this three same constants defining our recovery time steps. And then there are a couple of constants which need to be added in addition to what the R2D tool provides. We need the DS4 repair duration. This is something that was missing in previous versions of R2D. It might be updated now. And then you also define the maximum repair crews per building, the maximum residents per building, because what was happening to me that there are some very big buildings in this exposure data set. I was getting really high number of people populating a single building, so I just limited this in this constants file. And then you define what was the housing resource, this is shelter, and then what's the demand for repair crews, because R2D gives us the repair time and the repair cost from HAZUS, but we don't have the repair demand for workers. So we define this here, and all of these things are globally applicable to all the buildings. That's why they're defined as constants here. And this is something that is needed just for the R2D example that I'm looking at now. Then the content, as we said before, a single locality, all residential building components, information is provided from R2D. So how do you define this? Well, there's a single locality, components in locality are now defined by a bounding box. So instead of defining the centroid of the locality, we define this bounding box, which is going to limit the extent of region we're going to be looking at, because R2D in this example 1 covered a slightly bigger region. And then you define the recovery resource supplier, this is the emergency response center. And then here is where you hook up iRe-CoDeS to the R2D output. You can define the building's info folder for locality 1. It's You can also find this output on GitHub, so you don't have to run R2D for this example. You already have the results in the repository. They're here. And what R2D does, it gives you a separate folder for each building. And then in this folder, you're going to find the information on the building in terms of the building's location, footprint, area, and then also the damage information, initial damage state, repair cost, repair time, casualties, and so on. You define the buildings which you want to consider. And also because sometimes if you consider all the buildings, the calculations might be too long. So I put in this maximum number of buildings value here, so you can take a look at a smaller number of buildings and still run the calculations slightly faster and see how the code works. And then we also define what's the area per person. Here we use square feet. So basically a single person takes up this amount of square feet. This is how we get to the population of each building, because we don't have the population information right now in R2D. Damage input. There is a class called R2D damage input, which reads the information from these folders and then assigns damage states to components in pyrecodes. The only thing you need to define here is the scenario ID, because this is all Monte Carlo sample. There are a lot of results, probabilistic, of course, and then you define which scenario you want to look at. So you can run pyrecodes while changing the scenario ID, so you can also get the uncertainty bounds in these simulations. Resources, there are a lot of resources now, but luckily they're very simple to define. In pyrecodes, we have shelter. And once again, we define the distribution model, the parameters of the distribution model. Here we use a sort of very simplified distribution priority. It's called supplier only distribution priority. This means that basically every building tries to meet its own demand for buildings. This comes back to the assumption that people go back into the same building which they populated before the event. And no transfer services are needed. We don't look at the transportation system at this point. And then you define other recovery resources, which are listed here. There are a bunch. So for each recovery activity, we have a different recovery resource. And they're also distributed using the utility distribution model. And here you can see the use of another distribution priority class, which is called random priority. So here we shuffle the components randomly, and then we assign engineers in this way, because if you have, it wasn't clear to me how to better define the priority for buildings. And also if you have market-based recovery, this is going to be conditioned on the socioeconomic factors as well. This is something that we can work on in the future. You all can also define the seed for this random shuffling of components when resources are distributed, so you can have some consistency between your simulations. If you want to debug or look at the results, it's easier to track. And then we can go to the resilience calculator classes. Once again, we have the iRe-CoDeS calculator and the NIST calculator. And then define the main file. The difference here is that we're using the R2D system creator class, and we're using the same system class as before, and the link to where we located our JSON files representing component library and system configuration. Running pyrecodes is the same. The only thing that changes is where your main file is located. And then once again, Python script, the Jupyter Notebook, and Google Colab, it should all work fine. And then resilience assessment output is similar to before. Now we have slightly less output because the calculator looked at a smaller number of resources. And you can see, for example, meeting 95% of demand for shelter, or basically housing 95% of the population, took around 509 days in this simulation, in this scenario 1. And these are the outputs which you can get. Once again, you can take a look at the supply and demand for shelter, for repair crews. You can do the same thing for money, for permitting teams, demolition teams, and so on. It's all consistent. You can also have the Gantt charts here. Here it's slightly more interesting because we have more recovery activities, and they're all conditioned on resource availability. So, for example, this building here, it went through all the recovery activities quite quickly. And then around, let's say, 80th time step, or 80 days after the disaster, this building got its permit, but it was waiting for workers until almost 500 days after the event. Because as you can see, there is a big unmet demand for workers. So we can calculate, let's say, the average waiting time for start of the construction, or the average waiting time for building permits or whatever, using these kinds of simulations. And what we can also do, we can, because we have footprint information stored in R2D, we can also plot these nice maps. And this is all done by pyrecodes. If you have your own footprints and your own components, you can do the same thing. This is done in the GeoVisualizer class in pyrecodes. And here you can see how these colors change as these components are going through different recovery activities. This is because this is a GIF, which is made by assembling a bunch of JPEGs, which are created in pyrecodes. This is also done by the GeoVisualizer class, and you can also put on the right side certain supply-demand plots, so you can see how the supply and demand for resources changes as these buildings go through different recovery activities. And so now I'm gonna show a couple of examples for future development. At the moment, I'm structuring future development into two groups. The first one is what I called horizontal integration, where we're trying to integrate different regional risk models with pyrecodes. And here we can use, you can use different fragility curves, different ground motion models, which are more or less comprehensive. You can also use finite element models if you wish, as long as they are compatible with one of the system creator classes in pyrecode, or you can also write your own system creator class to get the data from other regional risk models. At the moment, I used R2D tool. I've also used OpenQuake, although this is not public yet, and Hazus is something that is compatible with pyrecodes at the moment. The other way of integrating things into pyrecodes is what I call right now vertical integration. This means we don't extend this computational workflow in this direction. We integrate other infrastructure simulators which have their own resource distribution models or their own recovery models. And here you can see what I'm interested in is integrating much better infrastructure simulators into pyrecodes, because right now they're a bit simplistic, and we're developing interfaces that are going to allow this to be, I would say, even more user-friendly. We can also talk about integrated socioeconomic models. This shouldn't be too hard. And what we're doing right now with the SimCenter is we're integrating the ReVet simulator into pyrecodes, and ReVet is special because ReVet simulates both the recovery and the water flow for water networks. And so we're going to be interfacing between pyrecodes and ReVet during this recovery phase, taking into account the fact that the building stock is going to have a changing demand for water, and that the water system is going to have the different abilities to provide this water over time. So this is one of the interdependencies which we hope to capture. And also we're going to be conditioning the recovery of components in the water system depending on the resources available, so workers, material, and so on. And also based on the transportation system, because we're going to be looking at the access to repair. And this is where we're going to also integrate the residual demand model for transportation. We're also looking at other models such as the spatial queue model, where we plan to use these models as traffic simulators. So we plan to rerun this traffic simulator at different points in time during the recovery phase. And then we can see how traffic is going to be changing as people are coming back into the cities and as you have more electric power or more water. And what is also interesting is that these traffic models are only going to be in charge of the flow simulation, so simulating the flow of cars, but pyrecodes is going to simulate their recovery. So if you have your own simulator which only has the distribution model inside, you can still use pyrecodes to simulate the recovery of components. Here is where you access pyrecodes. Pyrecodes homepage is what you see here in the background. This is the QR code for the homepage. This is the QR code for the GitHub repository. And if you encounter any bugs or have any problems, please let me know. You have my email here. I will be happy to check out what's happening and try to fix this. And then if you have any questions, SimCenter forum is also a place to go. You can open a topic there with pyrecodes in the title, and then we can also discuss problems there or future features of pyrecodes or some ideas for development. Visit the SimCenter website. They have other great tools apart from R2D. I think it would be interesting to check them out. And then if you want to take a look at R2D into a bit more detail, there are live expert tips on February 9th by Dr. Jinian Zhao, and there you can learn how to use R2D and then hopefully also extend the R2D to pyrecodes, which I just showed in this presentation here. So I would conclude now. I'm very happy to take any questions which you might have.
Fantastic. Thank you, Nikola. That was a lot of information very fast. So there are a couple of questions, but very well done. So thank you. Are the recovery functions made up, or are they from published research?
So they're mostly from published research. As I mentioned, I was using Hazus as one source. The other source is the FREC framework and REDI guidelines. What I had to sort of make up are the resource demands, because these are not usually defined in these kinds of guidelines. They usually only provide the time and the sequence of recovery activities. Apart from Hazus, FREC, and REDI, you also have other individual bits and pieces of information in different papers, which I also looked at and then tried to somehow adjust this input for my purpose.
Okay. The summary output is very nice, but can you also interrogate the resulting output, or is it just the summary that you showed?
So what I use to interrogate the output is by debugging, basically. I mean, because I'm not sure what users would like to see apart from this information. If you have any ideas, please let me know. I can change, I can tweak the calculator classes easily to show more information. So what I do right now, I run the simulation and then I open the debugging tool and I go into the system class where I have all the information about the components, the time step where they were functional, where they were recovering, and so on. And then this allows me to have a better insight into recovery. But for a user that only wants to run pyrecodes, this is the only information which they can get. If you want something more, just let me know. I think it will be too difficult to code it quickly.
Okay, that's a good lead into my next question, which is, this is complex software. You're a team of one?
Yes. For now, if you want to join, please. There are so many ideas, but I only have 10 fingers, so I'm happy to collaborate.
And so I guess the other question is how do I get in touch with you if I have follow-up questions? You shared that information already, but just to reiterate, you'd like them to send in an email as the current preferred format?
Yes. And do you see my email here on top right?
Yeah.
I hope you can. So yes, please email me. We can Zoom, and then we can talk more.
Excellent. This is all the questions I have right now. So I think we can probably wrap up the recorded portion. And for those of you who are here live, we can continue the conversation and questions after this recording. But Nikola, I want to say thank you very much for the presentation. This is very exciting software. We're really happy to be working with you and having it be available in R2D. Thank you to the attendees for joining this live session and for the questions you had for Nikola. As a reminder, you can register, as Nikola pointed out, for future live expert tips at our SimCenter website, which is simcenter.designsafe-ci.org. This concludes today's live expert tips. We hope you've been inspired to pick up the pyrecodes, adapt its capabilities, and incorporate it into your work. So thank you very much, Nikola.
Thank you.